Guys, now we've came to the fun part. We get to analyze mass spectra, and I get to drive you crazy for a couple of more hours. Well, maybe not hours, but you get the picture. All right, so we need to take a look at fragmentation. Why is this stuff so important? What can we determine with it just by looking at it without relying on a software piece or a database, right? So fragmentation is really referred to as almost like a fingerprint. You know, this is something that we talked about with infrared spectroscopy, right? All molecules are different in their slight own way, even if it's just one extra carbon. And in the fingerprint region of the infrared, we saw different things that could happen. And maybe our eyes, and we could not determine those differences in the very beginning, but a database system would be able to very easily. Well, fragmentation patterns with a molecule is kind of like a functional group in infrared. They're very specific. So molecules will fragment their own way, and no other molecule will fragment in the same exact way. And because of that, this is really a fingerprint. And we can put these things into a database and we can cross-reference them very easy. So the good thing about mass spectra here is that we can ID a molecule. That's why we use it. Now, I say that, and I'm kind of say that very light-handedly, but you know, this is pretty powerful stuff. Let's think about it. Let's say that you were running a sample, and this was a truly unknown sample. You had no clue what was in it. And you run it on something like a GC system or an HPLC system that separates the components out. And let's say I get a component here, and I get a component there, and I get another one here, and another one there. But these chromatography systems do the separation. So each one of these components will eventually go into the mass spec. So each one of them, one at a time, as they come off of this chromatography system, will go through the MS to get analyzed. The mass spectrum fragments those components one at a time as they come through. And it will look at fragmentation pattern. So here is my MS M to Z ratio, and I maybe would see something that looked like a series of lines. So let's say it's this last one that I'm looking at right here. That one goes through the MS, it gets fragmented, and now I get these lines that show up on the mass spectrum. These lines will tell me how the molecule is broken up. And only that molecule will break up in that way. So it uses a database, and it looks at this mass spectrum, and it compares it to the database, and it will be able to identify that compound based on the mass spectrum that it received. And it will tell me, hey, this compound is cocaine. THC. I mean, mass spectroscopy gets used all the time in drug analysis. Well, let's say that I did not have a mass spectrometer. I didn't have that technology at my hand. Well, the problem is that I could still do the separation up here at the very top, and that's kind of where it would end. No mass spectrum would come into the system. I don't have that piece on there. Well, what is this piece? Don't know. How could I find out? Well, I hope that I would have a general idea of what would be there, because what would have to happen is that I would have to have a series of standards. And these standards will have to be injected one at a time for me to see if they will come off at that location. And if they do come off at that location, then it doesn't mean that it's that compound. What it means is that it comes off at the same time. I'm getting closer, but then I would have to take more steps to kind of prove that that standard is that peak that came off of the chromatography system. Get it? It's a lot of work, especially if I have no clue what would be present. And let's say that I have a standard and I think it's what it is and I inject it, but that standard comes off at this location, not in spot number 4. I'm going to have to go do the whole thing all over again. Choose a different standard, run it, see if it comes off at the same retention time. If it does come off at the same retention time, make a note of it. Then I go back and I do some more tests. Maybe I need to do more analysis on a different instrument in order to confirm the identity. But you know what? With mass spectroscopy, all of those worries go away. Mass spec will take that compound, it will break it up into fragments, it gives me fragmentation patterns, it matches it to its database, and it says, ta-da! This is that molecule. No more worry. So I can use it as an identifier, and I want you to appreciate that, because this could make our job much more difficult if it could not single-handedly identify a compound. Now, something else that we need to talk about with the mass spectrum is that almost every single time we use what we call nominal mass. Nominal mass is just a fancy way to say whole number. That's it. So, for instance, if we take a look at water, water's H2O, and that's typically an 18.02 gram per mole formula weight or molecular weight, right? Well, mass spectroscopy will typically chop that off, and it will give me the whole number, rounded whole number at least. All right, so we're looking at whole numbers, and we would refer to this as 18, not 18.02. Now, I'm not saying that we cannot record decimal places. What I'm saying is that typically that is not what's done. Okay? More terminology of the spectrum before we go any further. Let me move this back up. We have a mass spectrum, and I see a line and maybe a bigger line here and then some there and some there. Let's say that this is my MS, M to Z ratio and abundance. So I'm not even going to do anything there. It's just a signal. There's some terminology here that we want to talk about. The first kind of term that we need to introduce before we start analyzing these things is the tallest. There's always going to be a tallest fragment peak or signal. That tallest one is what we call the base peak. We call it the base peak because it is the most common fragment that is associated with that compound. We also call it the base peak because this is typically the one that is ranked at 100, and then everything else is scaled according to that one. So this is kind of our foundation. But the tallest peak is called the base peak. It is the highest abundance. So there's going to be some questions, maybe in some mass spectra, that I'll say, what's the base peak? That's all that you got to do. Go through, look at the MS spectra, figure out which one's the tallest, and report that as the base peak. That's it. Pretty simple. You shouldn't get those questions wrong. Another peak that we want to take a look at is the furthest one. This is the one that has the highest M to Z ratio. Actually, this is the formula weight of the compound. No fragments. This is the compound going through. It does not break up. It stays together. It just loses an electron. That's all that happens. And that piece, not really a piece, but the whole molecule, is registered at the collector plate. That is the highest M to Z ratio that I have. This is what we would call the parent peak. If some people do not use the word parent, then other people will use the word molecular. Molecular they like a little bit better because that refers to molecule. It is the whole thing. So the parent ion or the molecular ion. Either one. I typically use the M peak. I abbreviate the word molecular to M. Many other people do that as well. And they refer to the M peak. The M peak is the highest M to Z. Now, do not forget, we're not looking at this tiny little peak that's right there beside of that major one, because that tiny little peak is coming from isotopes. That's not what we're doing. Isotopes are there. They're present. They're in very small amounts. We're going to see very tiny peaks that are associated with them for the most part. And we're not using that as the M to Z for the M peak. It's the one that's kind of dominant there on the end. Don't go by the tiny little bitty ones that are to the left or to the right of it. Now, let me give you kind of an idea of what we're talking about. So here's a mass spectrum. And on here, we see a M peak and a base peak. The base peak is always going to be very easy. The base peak is, of course, always going to be the tallest, and that's what we're seeing right here. It's taller than all the other ones put together. And because of that, that is the base peak. And if we go down and figure out where this crosses the x-axis, this crosses at the M to Z, right, of around 43. It's actually listed right up here at the very top for us. Well, keep in mind, M to Z is mass to charge. Most of the time, it is a +1 if we're not doing anything screwy to the machine. And this is also the formula weight or molecular weight of that fragment. So this fragment weighs about 43. Well, here's an M peak over here to the side. Look, right here. See that little bitty thing? That's from the isotope. Do not count that. That is not major, right? We see one fragment that's basically held up right here in the very end. And there's a little bitty peak that's right above it. And some people will say, well, how do I know that's not the M peak? That's a little bit higher than this one. No, isotopes are present. Isotopes will be there. They're in very small amounts. And because of that, you ignore that they even exist. This little cluster right here, this is probably due to isotopes. This is kind of the main one out of that little cluster that's happening. So this is going to be my M peak. That is the fragment, not really a fragment though, right? This is the whole piece that's coming through. The reason that we're calling it a fragment is because it is a piece. It's missing an electron. And I know it's just an electron, but it's missing something. It's missing a tooth. It's not the whole thing as it went in. So by definition, it is kind of a fragment. But that's the whole compound as it stayed together. And the whole thing weighs 72. Again, nominal masses here. 72, 43. That's my M peak, and that is my base peak. I also see all these other fragmentation patterns that are happening here. These numbers are listed on them, 57, 29, 27, and 15. All of those are different fragments that exist that are very common when this molecule begins to break apart. And here's the molecule that I injected into the MS in order to get the spectrum. Now, we're not going to talk about where these other fragments are coming from, not just yet. That's not the purpose of this slide. We're just looking at really what's present and some terminology that I can take away before we go further. Notice over here to the side we see relative abundance. It says relative because it's relative to something. What's it relative to? It's relative to the base peak. So here's the base peak, and that's at 100. That will typically always be 100. So if you get statistical breakdown like this with the MS system, look for this 100, and that 100 is probably going to be due to your base peak right there. If I look at the 72 was our M peak. Look, 18.56. That's pretty big. Well, I compare that to that little bitty 73 right there. 0.52. That basically means squat. Look, it's the shortest one on the list. Don't use that as your M peak. I can't say that enough. Don't get confused with that. So this is the parent peak, or the molecular ion peak that comes from it. So I would call this the M peak. All right, so with that said, I'm going to flip the slide on you, and we're going to zoom in. And this is a zoomed in version of mass spectra. Now, it is not the same molecule that got injected here. This is a different molecule. How do I know that? Look at the formula weights. Look at the M to Z's. 860s, 861s, 862s, right? This did not have that. This only went to 72, and that was it. So this is a different molecule that was injected onto a mass spectrum, but we zoom in. And what we do is that we zoom in maybe on this area. And to us right now, it looks like little bitty lines, but they're not lines. It's actually a peak that shows up. Not only that, but the reason I like to show you this is because look up here at the very top. 860.531, 861.529, 862.526. These are not nominal masses. They're not. That would have meant whole numbers. We have mass spectra systems that can go greater than whole number without a problem. Most of the time we don't need it, though. Most of the time, as long as we know the difference between 861 and 862, that's all that matters. But there are systems out there that are a little fancier, they're a little bit more expensive, and they can carry that formula weight, or the M to Z ratio, further than a whole number. Why would you need it? Research, development, really making sure the fragmentation pattern is going to be different. If you've got two compounds that have similar fragmentation patterns, but one is slightly off than the other one, then this, more power to you. You probably do need something like that. But for the most part, working in a laboratory, routine analysis, nothing fancy or crazy going on, nominal masses are fine. But there are ones that have this type of resolution. All right, so with that said, I'm stopping this video. We're going to come back. We're going to pick up our discussion with mass spectra, and we're going to start dissecting these things piece by piece by piece.